Good morning. My name is Eric Reese. I'm the Senior Vice President of the Memory and Storage Strategy Group at Kioxia America. It's my pleasure to welcome you to this keynote presented by Kioxia. First, a little bit about our company. It's now been a year since we've become independent. When I was at this conference last year, I had the pleasure of introducing our new name. We've now had a year of people being able to practice pronouncing it. And finally, serious word about our mission, which is to uplift the world with memory. We are involved in many different areas of memory, particularly storage. But the thing that I'd like to highlight today is that we are the inventor of flash memory, and our intimate knowledge of how that works and the potentials of the media are what are underpinning the software-enabled flash technology that I'll be talking about today. In our data-driven world, non-volatile storage plays an enormous role in pulling all of that data together. But within that non-volatile storage, solid-state storage has been playing and will continue to play a larger and larger role in managing the data that is being collected. Within that, the hyperscale data center is a dominant player, and they use storage differently. Last year, I talked a lot about that, particularly how their data centers are application-driven, which by extension means software-defined. I also discussed how flash itself is a digital media, and there's some incongruity in flash hiding that digital nature behind the paradigm of the hard disk drive, in which we have been doing for many years up until now. It isn't the time to consider something different. Well, I'm happy to be able to talk about that today. The hyperscale data center does dominate storage, particularly solid state storage. And within that thought process that I mentioned of it's being digital, the data center being software driven, there are many opportunities that are yet to be addressed. And it is those opportunities that I'd like to talk about now for the next few moments. The first of those would be latency. So latency is obviously something that we're all continuing to try to drive down. But as you do that within the traditional solid state storage, every once in a while, you'll get an outlier. One way to deal with that is to slow things down and bunch them together, particularly if you have a workload that is particularly latency sensitive. So of these two options, which is better? The smart guys out there will say it depends. And of course, you're all the smart guys. Depending upon that workload, you may want to dial it down. You may want to be able to position things for speed. And the application needs to be able to make that decision. Another opportunity is workload isolation. We've all lived in an environment where you really want to isolate yourself from that noisy neighbor who may be pounding on his drums or doing something else. In the data center also, you may have a chatty I/O that can interfere with other streams, and the ability to isolate those streams. And in fact, in today's world, thousands of streams that are coming in simultaneously is another opportunity. Flexibility is another opportunity that is of extreme value. In the data center, you may be running different kinds of, in fact, you will be running different kinds of workloads in parallel, simultaneously. And the simultaneous model is probably the more likely one. One opportunity that has not yet been met is to be able to make the solid state media dynamically reconfigurable to best meet the needs of the workload that is coming through. Low-level control is also an item that is quite important. Now, some of you may be saying having low-level control over my media is something that I need like a hole in the head. But when you're trying to tightly orchestrate things within the hyperscale, there are some things that do need to be controlled. How you place your data, when you start and stop garbage collection, how you manage your ECC and RAID. These are some of the features that are typically low level that need to be managed. And that needs to be done in a way that doesn't tie you to a single vendor or a single technology. Now, because these are real problems, there have been different attempts to address them in the market. Some of them have been trying to modify a traditional drive. Well, it's really hard to take a minivan and turn it into something different. And there are people who really don't want to take a box of nuts and bolts and make something customized. So there really is a need for something different, and that is software-enabled flash. Now that we've talked about the opportunities, let's talk a little bit about what software-enabled flash is and how it will address those opportunities. Software-enabled flash combines the speed and flexibility of flash with the ease of software definability, with the objective of maximizing the potential of the flash that is already being deployed and will be deployed. And it does this in a way that we think will allow you to have your cake and eat it too. Software-enabled flash fundamentally redefines the relationship between the host and the solid-state storage. It does that by giving the host unprecedented control over the behavior of the media and the device. In other words, it maximizes the value of the flash. Now, we do that through purpose-built hardware and a flash-native API. The API is represented on the left, the hardware on the right. This API is flash-native, and that is where you will see most of the definition of the behavior being controlled. The purpose-built hardware is focused on managing the media and dealing in an abstracted way with the low-level functions we talked about. In the case of the software, as I said earlier, it's flash-native, meaning that the API is written and designed to be able to give control over the key behaviors that the data center will need in addressing isolation, flexibility, all those opportunities that I talked about. Furthermore, with the hardware, not only are we giving abstracted control over the low-level functions that I talked about, but also, if you'll notice this magenta arrow talking to DRAM, we allow flexible deployment of DRAM. Depending on the need of the host and of your data center, you can deploy DRAM anywhere from 0 to whatever is needed based upon the type of devices that will best fit your operations. Now, we talked about software-enabled flash being different and providing different things and addressing these opportunities. So let's talk about what those opportunities are and how they're addressed. Abstraction is a key way that we do this by abstracting out the hardware functions that are listed here, as well as giving software abstraction to key behaviors. Isolation being one of those most important ones that we provide, one of the most important features that we provide. Now, we allow isolation on 2 levels. One is through hardware isolation, where you can break up your quanta of flash into various virtual devices. And you can freely define what those virtual devices are. On top of that, we provide another layer of isolation, of software isolation, by being able to break those virtual devices into quality of surface domains. The capacity of a quality of surface domain can equal 100% of that virtual device, or some subdivided level of that. And this illustration will show that. Another key component is queuing, something that's very powerful in controlling your latency outcomes. We provided, as a default, 3 forms of queuing: priority queuing, round robin, or weighted fair queuing. As I said, these are provided by default, but the host has control over adjusting those weightings according to the need of the workload. Offloading is also something that's very powerful and important, and that's going to be offloading a lot of the media-related functions from the host, and particularly from the CPU. In the case of a write, once a write is assigned to a particular device, the software-enabled flash controller will scan the media and identify the most opportune or the most appropriate place for that data to be written to. We'll conduct that write and then return the address to the host. In the case of some of the low-level functions we talked about, such as garbage collection and others, again, the controller will offset from the host the actual execution of those functions while allowing the host to be able to determine when to start and stop. Those that include garbage collection, wear leveling, compaction, and others. Finally is the value to the business and the enterprise. One of the key objectives we have with software-enabled flash is by those who adopt the API to be relieved from having to use a technical term, rejigger your software to be able to fit with the most recent or the upcoming generation of flash. And an important factor in TCO is always being able to get onto that new generation of flash as soon as possible. If you adopt this API, you can do that because each generation of flash will just work. That will therefore allow you to reassign your resources to those things that are much more important to your enterprise. That obviously is, I think, difficult to overexpress how important that value is. Finally, as you continue to adopt, or as data centers continue to adopt flash over hard drives, the ability to dynamically meet the needs of that storage to the need of the data center will really aid in maximizing the value of what's being purchased and what's being deployed. Finally, I'd like to talk a little bit about the adaptability within the ecosystem of software-enabled flash. It is an open standard. We have it on our GitHub. I'd encourage anybody to go there, download it, look at it, and join the project. Also on the hardware side, there's a lot of flexibility or adaptability there as well. The software-enabled flash API is agnostic to the architecture of the flash. It can be MLC, it can be Kioxia. We're also independent of the interfaces. As I explained earlier, we have very flexible very flexible approach to the deployment of DRAM. And finally, ACF is not tied to any particular controller. So let me repeat again that software-enabled flash technology fundamentally redefines that relationship between the host and its storage, particularly the solid-state storage. It does that through an open source flash native API where the behaviors are defined. There's powerful offloading from the host CPU of the low-level functions that gives the host, that together gives the host full control and ease of use. Finally, let me talk a little bit about what else we're doing here in SDC. 11/20 today, Rory Bolt, one of the chief architects of this technology, will be going through the how of what I've described here, plus more. Tomorrow we'll be hosting a Birds of the Feather, and I would encourage you to bring your questions and comments and suggestions. We welcome you there. Finally, please go to our website, softwareenabledflash.com. Download the white papers we have there. That'll also be the software-enabled flash will also be the place where we will announce further updates and further developments. Finally, you will find the link there to the API, where I again encourage you to download it and join the project. Thank you for joining me here today in this discussion of software-enabled flash, which really is a paradigm shift in the way that flash can be deployed in the data center.